Hey guys, welcome to the video on basics of linear algebra. We will be covering matrix multiplication and matrix inverse in this video. Let's get started. In the first topic, we'll be covering scalars, vectors and matrices. So what is a scalar? Scalar is just a single number. For example, 1, 2 as shown in the video is a vector. So how many numbers are there? 1 and 2, there are two numbers, and therefore this vector is called two-dimensional vector, and the first index is 1 and the second index is 2. Similarly, in this example, we have taken x1, x2, so on till xn. We have taken n numbers, and therefore this vector is said to be an n-dimensional vector, and the first index is x1, the second is x2, and the nth index is xn. And vectors generally have a notion of direction associated with them. Now let's jump on to matrices. What is a matrix? A matrix is a rectangular two-dimensional arrangement of numbers. For example, this is a matrix here, 1, 2, 3, 4, 5, 6, right? How many rows are there? There are 2 rows and there are 3 columns, right? So this is what we call a 2 cross 3 matrix because it has 2 rows and 3 columns. For example, in this matrix, if you see, you have 3 rows and 2 columns, so it's called a 3 cross 2 matrix. So any rectangular arrangement of numbers is called a matrix, and if a matrix has m rows and n columns, it's called an m cross n matrix. Alright, and since it is a two-dimensional arrangement, you need two indices to exactly pinpoint a number. For example, if you take this element here, x11, it is present in the first row and in the first column, therefore it is 1, 1. Similarly, this element x12 is present in the first row but second column. This number x21 is present in the second row, first column, and this number x22 is present in the second row and second column. So therefore, given two indices, you can actually exactly pinpoint what matrix element it is actually referring to. And another very important definition in matrices is the notion of main diagonal. All elements which have the same row and column index is said to be belonging to the main diagonal. So let's take an example. So in this example, x11 and x22 have same row and column indices, that is 1 in this case and 2 here. So this actually forms the main diagonal of this matrix. Similarly here, this is the 1, 1 element and this is the 2, 2 element, right? This is the first row, first column, this is second row, second column. So this is the main diagonal here. And similarly 1, 6 forms the main diagonal in this matrix. With this out of the way, we can go and define what we mean by transpose of a matrix. Transpose of a matrix is nothing but mirror reflection about the main diagonal. In mathematical terms, we say that A transpose of ij is A of ji. Here you can see this mirror reflection. But let's come to an example. Here, as we saw before, 1, 5 forms the main diagonal because they have the same row and column indices. And transpose of this matrix 1, 2, 3, 4, 5, 6 is actually this matrix. So let's see how this came about. This is the main diagonal, and we are reflecting the elements about the main diagonal. So therefore 2 comes here, 4 comes there, 3 comes here, and 6 comes here. As you can see, this is what we are getting here as well. So one thing to note here is the number of rows and columns also gets exchanged. So in this matrix, we have 2 rows and 3 columns, whereas in the transpose matrix, we have 3 rows and 2 columns. Quite important, right? It's quite simple as well. Now let's go to the next topic, that is, what do we mean by multiplying two matrices? So the matrix multiplication is defined as follows. You cannot take any two matrices and multiply them. There needs to be a compatibility condition that must be satisfied. So what is the compatibility? Let's take two matrices A and B, and you are multiplying A and B. If A and B matrices can be multiplied, it means the number of columns in A is equal to the number of rows in B. For example, if you take this matrix to be A, this matrix to be B, so how many rows are there in A? There are 2 rows and there are 3 columns. Similarly, there are 3 rows and there are 2 columns in B. So here you can see these two matrices can be multiplied because the number of columns in A is equal to number of rows in B. So that is the first condition that must be satisfied in order to multiply the matrices. The multiplication of two matrices gives a resultant matrix C, and the dimension of that matrix is exactly equal to the number of rows in A times the number of columns in B. So in this case, you have 2 rows and 2 columns in A and B respectively, and therefore the resultant product will be a 2 cross 2 matrix, right? Let's go and take a practical example. So we'll take the same example in the previous slide. So as we saw before, you're taking a 2 cross 3 matrix and multiplying with a 3 cross 2 matrix, right? A and B, and you will be resultantly getting a 2 cross 2 matrix, as this is the answer which is being shown. So the steps followed in order for you to arrive at the answer is also shown in detail. So let's analyze them step by step. The first step is to obtain the 1 1 index of the resultant matrix. That is obtained by taking the first row of matrix A with the first column of matrix B. So what do we do with that? So basically we take element wise product and then sum them up. So essentially we take 1 times 1, 2 times 2, 3 times 3 and add them up, and you get the first element. And you can apply the same logic to the second element as well. So for the second element, what you will be doing is you will just jump onto the second column of B. So you take the first row and the second column, and you will be taking the element wise multiplication, and then you'll be summing them up, and you'll be getting the first row second column index. Similarly, for second row first column index, you take the second row of A, the first column of B, take element wise product, and then sum the result. So in this case it will be 4 times 1 plus 5 times 2 plus 6 times 3, you'll be getting 32. And the same logic when applied to the last element, which is the 2 element, you'll be getting 4 times 4 plus 5 times 5 plus 6 times 6, which is 77. So this is how you will actually take two matrices and multiply them. So this logic can be taken and be extended without loss of generality across all matrices if and only if they satisfy the compatibility criterion that we discussed before. So I hope the matrix multiplication is clear. Let's go on to dot product of vectors. Dot product is defined to vectors which are of same dimension only. That is, they should be of same dimension. So for example, these two vectors x and y in this example, they are of same dimension. What is the dimension? It's 3 dimensional because they have 3 numbers, right? So they have 3 numbers, and therefore they are in same dimension. And the dot product is defined as taking the element wise multiplication and summing them up. So in this case is 4 times 1 plus 5 times 2 plus 6 times 3, which when summed up gives 32. And it is noteworthy that x transpose y is y transpose x, right? X transpose y is the dot product, and it is a commutative property because multiplying 1 with 4 and 4 with 1 is the same, and therefore x transpose y is y transpose x. That is what we call the dot product of vectors. So these are some important properties to remember. Let's take 3 matrices for example, A, B and C. So A times B plus C. So first sum up B and C and then multiply with A. That is exactly same as taking AB and adding that with AC. This is the distributive property. This holds true even in the matrix cases. And this is what we call the associative property. That is, if you take 3 matrices A, B and C, and if you multiply them together, you can do that by first multiplying AB and then multiplying the result with C, or you can do the same by multiplying B and C first and multiplying the result with A in the beginning. Note the order is very important, and AB is not equal to BA in this case. Multiplication of matrices is not commutative. And let's go on to the transpose properties. So if you take matrix product AB and take the whole transpose, this is exactly same as B transpose times A transpose. That is taking transpose of B and multiplying it with A transpose. And transpose is again taking 2 times transpose will give you the same matrix, because transpose by definition is just reflection about the main diagonal. If you reflect 2 times, you'll be getting the same matrix, right? With the main properties out of the way, let's go ahead and solve a problem and understand some main concepts of linear algebra from that, right? Let's take a simultaneous system of linear equations. This system of linear equations is in 3 variables, x1, x2 and x3, and we have 3 equations. So let's try and solve them. So before solving them using the traditional high school method, let's write them in the matrix form. So this is how we write in matrix form. Using the rules of matrix multiplication, we see that 4x1 minus 2x2 plus 3x3 is 1, which is exactly the first equation we saw before. 1x1 plus 3x2 minus 4x3 is minus 7. Now we need to solve for x1, x2, x3. So is there any way of doing that? So if this matrix is taken to be matrix A and this variable vector is x, then you can write this as Ax equal to some vector, right? If this can be done, if there is some notion of inverse, so that you can write x equal to A inverse B or x equal to 1 by AB, something like that, we'll be understanding the notion of inverse in the next coming slides. So before understanding the inverse, we got to see what do we mean by identity matrix. So identity matrix is a matrix when multiplied with another matrix, it doesn't change the matrix at all. So in this case, if you take A to be any n row matrix, right? So if you take an n cross n identity matrix and if you multiply with that matrix, you get A. For all A, any matrix A you can take, Then if you take the identity matrix and multiply it with that, you get the same matrix. So identity matrix does not change the matrix at all. So what type of matrix can IN be? So it turns out that IN is actually a diagonal matrix, which means it has elements only along the diagonal, and on top of it, it has all diagonal elements to be equal to 1. Alright, so for example, if you take I2, a 2 cross 2 matrix, and multiply with any matrix which has 2 rows, you will be getting the same exact matrix in the output. Alright, there will be no change at all. So now we define matrix inverse for any matrix A. Inverse of a matrix is defined such that A inverse times A is identity matrix. That is the matrix that you need to multiply before A in order for you to get an identity matrix. Let's apply this idea to the system of linear equations we saw before. We first saw that the linear system of equations can be written in the form of Ax equal to B, where A is the matrix, X is the vector of variables, and B is the constant vector. So let's pre-multiply A inverse on both sides. As we saw before, A inverse times A is an identity matrix, and here you get A inverse B, and identity matrix will not change the property when multiplied, therefore you get the same X out here. So the solution for the variables is given to be A inverse times B. So Ax equal to B, the solution is X equal to A inverse times B. So if we apply that logic to the system of linear equations before, so this is the system that we had, and this is the matrix A, and A inverse can be computed using many methods like Gauss-Jordan, but we will not be covering that in this video specifically. For now we can assume that A inverse is given to you, like you can calculate A inverse, and this is the A inverse of this matrix. And once the inverse is calculated, if you multiply with this vector 1 minus 7 phi using the normal rules of matrix multiplication, you will be getting the solution to be minus 1, 2 and 3, which means x1 is minus 1, x2 is 2 and x3 is 3. So this is the notion of inverse. Alright, so now let's go a step further and try and answer a question. So does inverse of a matrix exist all the time? This is a very important question to answer, but unfortunately it is a clear no. Inverse does not exist for any matrix. There are some conditions which the matrix must satisfy in order for an inverse to exist. Those conditions are: A must be a square matrix, and there is no definition of inverse for a rectangular matrix, right, when the number of rows and columns are not equal to each other. So a square matrix with number of rows to be equal to the number of columns can only have an inverse, and on top of it, not all square matrices can have an inverse. Another condition is the rows and the columns must be linearly independent of each other. So what is linear independence? Hang on, we will be covering that in the next video.